Today we will continue, and there's one point that I like to recall because we mentioned different times, and membrane reactor is the case in which you will find in literature a lot of tentative to try to analyze the system with some more accuracies than in the past using what we call new metrics. New metrics means that today we are analyzing the membrane reactors in the logic of process intensification. Process intensification is something that is a little bit different in terms of strategy related to the traditional way in which we analyze the normal process, normally in process engineering, which is to have a better understanding of the benefits and to have a better control of what the process intensification means, the possibility to introduce some new metrics that are more consistent with the principle of process intensification is important. You will not find too much in the literature if you're looking into this kind of aspects, because this is still something that has to be introduced. And people don't like to change, particularly the industrial level, because that's something that is important, industrial level, what they've been doing until now. But slowly, this concept is becoming important, and the industry are understanding and using and evaluating this kind of approach. Two typical examples that we are using in membrane reactors is what we call a mass intensity and energy intensity, which are very much related to what we are discussing. Definition of these metrics are here. For mass intensity, we have this kind of definition. The total, for example, assuming we are working on hydrogen production, which is a typical case, total hydrogen fed and produced by the reaction. As we saw yesterday, we have to consider the hydrogen we supply, and if there is a reactor, there is a conversion, and also the hydrogen we are producing has to be considered, 2 divided by the total inlet mass. So a very specific ratio between the hydrogen, which in this case the product we are considering, that is fed and is produced, compared to the total mass that we have in the system. And that if you just go through, this is the definition where you have to introduce just the different molar fraction of all the components that can be present compared to the total mass that is present. That's what was concerned the mass intensity, and something very similar is what we call energy intensity. Energy intensity will be the total energy produced or consumed, because we can also consume the energy, by the reaction, compared to the total hydrogen fed and produced by the reaction. So the total energy compared to the total hydrogen that we are supplying. And so we refer exactly to the product that is at the origin of the energy production, but the total energy produced divided by the total hydrogen that is produced by the reaction. And also here, this energy intensity, independent, that can be the same definition, can be for a traditional reactor, by the way. This has nothing to do with membrane reactors. This has to do with any kind of system. Traditional one or a new one is the same. Normally, no one has been using in the traditional reactor until now because there was no necessity, there was no process intensification strategy to be eventually verified, etc. Today, we like to do because we want to check if the process intensification is real present or not in the system. And for doing this, we have to refer these same metrics, obviously, in the traditional reactors and in the membrane reactors, and we will make a ratio between the two parameters, the new one and the one related to new one reactors and the one related to the old one. So we can define independently for the new or for the bad with no problem. That can be this fraction of CO for the traditional one or for the new one. No difference at all. Obviously, with or means one of the two. You don't do both of them, but one of the two depending if you are considering the traditional or the other one. That's a typical case in which you can have some you can plot your mass intensity as function of the temperature. So here you have mass intensity, here we have the energy intensity. And what can be interesting, if you, for example, you look in a certain temperature range, around 350, 380 degrees centigrade, you can you can have the situation for the traditional reactors, and you have the situation for just the membrane reactors. As you can see here, that if you change now in measuring your mass intensity, also the pressure in the system, you have, as we saw yesterday, a significant change in the mass intensity. And that is interesting because from this kind of plot, that is true for mass intensity and can be true also for energy intensity, you can see that there is, first of all, in both cases, this plot is going to a maximum, basically, around 350, and that is the most interesting area. In both cases, for traditional reactors and membrane reactors, we have the best value. However, from this kind of plot, you can also realize that changing the pressure in the system, we can have the same behavior in a membrane reactors at much lower temperature than the one necessary for having this mass intensity in the traditional one. Basically, you have 320 and with 5 bar or around 300 degrees centigrade at 10 bar. That means this plot here, this one here, or this one here, you can have the same level of mass intensity or energy intensity that you can have with traditional reactors at 350, 380. Okay, so this is one of the ways in which you can represent the situation, and just making clear in evidence, in the case of the membrane reactors, the effect of the pressure, that is no effect at all in traditional reactors, because this is a kind of reaction in which we are talking here water gas shift, in which there is no change in number of mole between reagents and products, so independent from the pressure on the Le Chatelier principle, and just different situation we have in membrane reactors. Okay. Again, you can also have this, as I was mentioned before, you can try to have, in equilibrium state, by the way, is the situation in which you can try to understand how the system works, making a comparison from this mass intensity in membrane reactors and traditional one, and this ratio is the one that we like to normally to verify. We like to see the gain, the advantages of the membrane reactor compared to the traditional one, and this kind of ratio is the one that can normally is utilized. In the case when the ratio is equal 1, it means that we are in condition of equilibrium, and that's the normal situation that we take as a reference in this kind of analysis. So remember that when we write this ratio is just nothing more than mass intensity or energy intensity in the membrane system compared to the traditional one. And this is typical some example again, where you are plotting the ratio and not the situation that I was not the single units. And so we have a term of reference that when everything is equal 1, and we have situation in which you can have values of this ratio higher than 1 or lower than 1. And what you have basically to extrapolate, and if you make all the calculation, you will see that there is no way for traditional reactors to overcome these limits in line 1. That's only with membrane reactors you can have a situation in which this ratio is higher than 1, which is a situation that is showing the benefits of working in this situation. That you can make a lot of this kind of evaluation. Now you have higher than 1 and the second is less than 1. A ratio equal 1 means that the MR allows the attainment of the best ideal performance achievable by a traditional reactor operated in the same condition. Values greater than 1 indicate that the process carried out with a membrane results more intensified, and this condition can never be obtained by ATR. If you make more of this calculation in a different way, you can have the effect of the GKSV, that is gas hourly space velocity. That is a typical parameter that chemical engineers are using to evidence the benefits on mass intensity or energy intensity, and that is the ideal values that are presented and in a certain temperature. And again, you will have always the effect on the membrane intensity of both membrane reactors or traditional reactors is increasing the gas hourly space velocity. But end of the story, there is a lot of this kind of evaluation you can do it, and you can do effect on the feed molar ratio, etc., etc. But what is an interesting conclusion is here. If you just now to compare, for example, in terms of energy intensity as function of mass intensity, and you summarize all the different results that you can obtain, you will see that all the values for traditional reactors and the value for membrane reactors in some ratio, in a certain range of values, they are the same, they overlaps, and they are in the same area. But if you go to the ideal one, what we are really looking for, that means higher value, more than one, and in both terms, in both mass intensity and energy intensity, the only way to have good values up here is only with membrane reactors. The most desired values that can be reached are only by MR. There are some areas in which the system is competing, but there are areas in which there is no competition at all. That is important because there are situations in which you don't have to change your reactors. If you want, there is a situation in which if your output in terms of mass intensity or energy intensity is supposed to be in this area for different reasons, you don't expect more, etc., it's not necessary that you change your reactors. But if, as expected in most cases, you want to have a better results and you want to improve the mass intensity or energy intensity, and this kind of the result, you put together all these analysis and simulation that today researchers have been doing, in most part of the data you already find part in literature, only the membrane reactors can offer you this opportunity. Okay? And this way of, this kind of presentation using this kind of new metrics is the best way to give a vision and a strategy about the situation. So that is the story of these new metrics does not finish with mass intensity and energy intensity. If you go in the literature, and eventually I will send you, you will receive some papers, we are just enlarging this kind of discussion and, for example, introducing some new other parameter in terms of some process intensification parameter to characterize the same behavior in terms of footprint, for example, space really occupied for your process, for your system. Years ago, that was no important. No one was taking care of the space of your plant. There was a lot of space available. If you was not near home, you were going some other country where there is more space. Today, these things don't happen anymore. There is very few countries where they're having space available and they're ready to accept crazy old plant, where there is 1 square kilometer instead than 1,000 meters necessary. And so this kind of logic are becoming important. And flexibility. So there is a lot of these new metrics that were not important in the past, and today we are assuming a real cost. Flexibility means, for example, that today, if you analyze how the things are changing, you will see that in the past we were introducing new technology, and this technology were sitting in the place for 20 years, 30 years. Plant was a long life that, in front of them. Today, these things are changing much faster. Sometimes every 5 years, so less, you have to change technology, or you have to change the size of your plants. In the old situation, changing the size, the productivity, the size of the plant, well, the only way of doing was to take the plant and put it in the garbage and building a new one. And that was a nice way to lose money, etc. Today, there are new technology in which, and we are talking because membrane engineering is a typical case, if you want double the productivity of reverse osmosis units or gas separation units, what you do is just to double the number of the module. Eventually, if necessary, you have to increase the power of your pump, because if the configuration is more complicated, but for sure you don't have to change the system. You don't have to put in the garbage the previous plant. The scaling up and scaling down of any of these new technology is much, much easier and faster than any other existing technology today. And that can be measured. For doing this, we like, because we are working in the field, but you have to measure and to give a number. So you have to introduce a matrix that does not give you only mass or energy intensity, etc., but also some quantitative evaluation of what we call flexibility or eco-compatibility or footprint of the system, etc., in terms of productivity and so on. Okay? People don't like to change their mind and what they learned at school when they were students, and that's why this will take time, but it will happen, and that's why we are teaching and trying to suggest you. Just a few examples now, what can happen based also on membrane reactors, and what can happen in general in some new field, in which we want to rationalize full industrial process, introducing more and more integrated membrane operation. We saw something similar, and we will discuss before the end of this class a typical case in water, in desalination, etc. I don't know if you are aware that today desalination, if you were in Jeju last week, when I was, instead of being here in your class, people are already assuming normal to have integrated membrane operation, for example, in desalination, which means you don't have only reverse osmosis. You have all pretreatment to reverse osmosis based on microfiltration, ultrafiltration, nanofiltration, and similar. And now you have also the post-treatment to reverse osmosis to increase recovery factor, to keep control of the brine disposal as membrane distillation, membrane crystallizer, etc. This is becoming more and more obvious. Pre-treatment is a standard now. It's a part of the dominant technology, and post-treatment is not yet standard because membrane distillation, membrane crystallizer are still in a development phase, but people are discussing about this all around the world, including, as I mentioned a couple of times already, Korea. So some of these projects were just presented by Korean researchers, basically. There is other field very, very important in which the same approach is possible today. One of the most interesting and becoming more and more interesting is petrochemical industry. Petrochemical industry has been always a very conservative industrial sector. If they need money, they charge you, they increase a little bit the cost of the gas you pay when you go in the station, and they solve all the money problem, basically, because it's easy for them. We pay, and there's a huge immediate effect on the income for the company when you just increase the cost of the product, the major product they sell as the gasoline. But also in this area, things are happening. This is the one case interesting that we have been studying already a few years ago together with the largest producer of ethylene. Ethylene is one of the most significant industrial production today. There are a lot of plants around the world, and as the water is an important product, ethylene is another important product because it's at the origin of all this family of polymers, etc. So it's quite significant. And normally, ethylene is produced by cracking of these naphtha or some heavy oils, and you start your process. And later on, there is a lot. When you move along petrochemical industry, you see huge installation, a lot of distillation tower, a lot of flue gases in the air, and normally the control of the environmental impact factor, eco environmental impact factor is very, very severe, difficult, and expensive. So people are going, if you read the newspaper in Italy, where big fighting, big problem, we had to shut down some company that were not operating correctly, and they had no money to operate because it means to change everything, and they're just to shut down because now it's clear that the impact on the health of the people does not happen in one day, in 1 hour. nothing, you don't realize this, but if you make statistic analysis on what is happening in 50 years, in 80 years, on the population living in some area where you have a lot of this effluence around, etc., you will find a lot of situation out of the standard. It means there are peak in some disease, etc., that are clearly related to the environmental situation, etc. So more and more people are considering that we have to try to redesign, eventually for them spending not too much and to produce in the right way. Here is a typical example where we have been working, and we are working on the redesign of the production of ethylene. That means all the petrochemical industry basis, introducing all the existing well-developed membrane operation exactly as it has been happening already in the water system. Much more complicated here than in the water, but exactly the same approach. And also here, you'll see we have to analyze not just in traditional terms, but with the new metrics to understand a little bit better. This is quite interesting because the most interesting part here is that all the cracking will disappear. If you read newspaper, you will understand that more and more gas will be used in the future, much more than just oil or naphtha, etc. So the possibility here is to produce your ethylene using a membrane reactors. This is just membrane reactors where you are entering with your gas, methane, for example, etc., and you have started to produce ethylene, and after all the following will be just membrane filtration, microfiltration for some cleaning of the, if there is some caulk removal, etc. And there is again membrane contactors for removal of acid gas, membrane contactor for water purification. Here is gas separation units for the separation of these aromatic for the, the ethylene, the saturated, the ethane, ethylene. Same here, propane and propylene. And here there is hydrogen recovery, and we discussed all this time how it's relatively possible with zeolite membranes, or or with palladium membrane. These are industrial already. And just clean up, separation of CO, and just you can have a pure hydrogen going eventually for big fuel cell installation, etc. Basically, all the different steps, including here still surviving one distillation unit, but also this distillation unit will probably disappear because when you start to redesign, also here then you can have just a membrane distillation unit eventually, or other kind of membrane system. But you can see here basically everything here is based on membranes, and when we wrote this thing, that was a long time ago already, 10 years, we have no developed yet membrane condenser. Today we have a system that you can have membrane condensation substituting the traditional condenser. So if I have when we will update this kind of work, we will include here membrane condenser, and in more than one step here there will be the other membrane units. So that is the basic idea. Based on what? That is based on the fact that in that time that some new membranes were appearing, and that was the perovskite membrane that we mentioned a little bit. And perovskite is quite interesting because, today the cracking process is energy capital intensive, so they are quite expensive basically, and that is now highly endothermic reaction, and you need a high temperature, big, complicated furnace, cooking, etc. You can just try to reduce this. Instead of cracking, you can have a catalytic process at much lower energy consumption, and that will be ethane oxidative dehydrogenation. And how that can be done? That can be done by, that's the reaction we are considering, is an exothermic and not equilibrium limited reaction. And there is no need for steam. That's a long-term stable, is cooking limited just by oxygen, and much less investment. The situation is this one, that you can just if you have a membrane in which just you can supply, you can have in your system, you can basically supply oxygen, and this oxygen is coming from air eventually, and that is a perovskite membrane where all the petrochemical companies decided to work in. You have to separate the oxygen from air, not using a cryogenic system and cryogenic distillation, but using a perovskite oxygen conducting membranes. that oxygen selective membrane, where the only trouble that we have today, and still, that was for sure when this work has been done, but still today you have to operate at a relatively high temperature. And this high temperature is not for the temperature, not the energy involved, that's not a big problem, but is the stability of the membrane, the production. This is a huge plant, not small plant. And if you have to glue your membranes at this level of higher than 700 degrees, can be 800 degrees, 900 degrees, is not so obvious how it can be done for a long time installation, etc. But there's a lot of work in progress. If you do this, you can have this situation which you can just separate oxygen from air, supply your oxygen to the gas entering, and you just go ahead with this kind of interesting reaction. Problem exists, but no, you have a much easier management of your heat, the energy, heat and the thermal energy available. You can directly feed to the membrane reactor from the air, and much more safe than the alternative system. Now, for a correct evaluation of making sense, it's better to use this kind of system or the traditional one. You first of all, instead of doing energetic analysis, you have to do exergetic analysis. Exergetic analysis, we also mentioned it a bit, you never made it, but that is not a mistake, is exergy. Exergy means that we are calculating not the overall energy that you have available, but the good part of the exergy, of the energy, the one that you can really transform in work, which is the total minus the entropic losses, basically. There is a form of energy, a part of the energy that is the entropic origin, that means second law of thermodynamics, not the number one. So it's not only the enthalpy, but it's also the entropy. And the entropic losses are the ones that are decreasing the efficiency in terms of your system. So what you have to do is to analyze, to make a correct calculation of the exergetic analysis. And that is what can be done. And if you do in this way, and you just study about the conversion and the selectivity of your system, and the traditional reactor is the yellow one, if I will remember, and the other one are just the membrane reactors, MR2 and MR1, the green, you will see that in terms of the selectivity and conversion, all the data are much more interesting. By the way, we are assuming, these are data from literature already, you are assuming that you are working on perovskite. And perovskite, that is the problem, is not something that you find that you can buy in the shops. So the people are still working a lot on the perovskite, and large-scale perovskite tubes take some time to be available, but is the way in which people more and more are considering, and they believe that perovskite will be soon one of the possible membranes available. Remember that perovskite has a very special kind of system. They are crystalline material, and there is no selectivity diffusivity mechanism here. There is no Donan effect here. Everything is related to the number of defects present in the crystalline structure. And when there is vacancy, defects of oxygen, for example, these perovskite are a mixture of metal oxide, and this vacancy, oxygen from the air is activated at the surface, jump in one vacancy, move to another one. So related to the number of vacancy means defects, you have the transfer of only oxygen who is jumping from one oxygen vacancy to another oxygen vacancy to another one. Okay? So that is totally different from what we know, but if you just make this kind of analysis in terms, for example, of efficiency, this is the traditional one, and this is the traditional one, when you go to the right good membrane reactors, this is the basically quite significant increasing. The kind of efficiency of the system is significant. Exergy losses is what we want to do, that is exergy losses. We want to minimize exergy losses because this is a good part of the energy that is not related to the entropic effect has to be lower. That's much lower than the one related to traditional reactors. So again, all these parameters are clearly showing the benefit you can have in this kind of system. Also here, now not only the exergetic analysis necessary. If you were in Jeju, your colleague from some company, I don't remember if it was others, were just talking in public, in this case, using exergetic analysis. 85% of the people were not understanding what they are talking about, but in the company already, not only the university, people are using exergy. And that's quite important and interesting, because in between, also that will be evidence how people are accelerating this transformation in the system. Also here now you can re-elaborate your numbers in terms of mass intensity, energy intensity, molar intensity, etc., and you can see here, following the same definition I gave you before, and in all the reactors we are considering the kilogram of the product that you are obtaining for kilo of ethylene, that is the point of reference. You can see that it's quite interesting, the transformation compared to the traditional reactor, that's the situation, this and this, and this one is the most interesting one. The MR2 is the most interesting one we are considering. And the same is in molar intensity, which is just another kind of definition. And if you just want to have the same kind of consideration related to the amount of air required to produce the amount of oxygen necessary for the conversion in your reactors, and that's why you have all the number for doing this kind of calculation. Again, here mass intensity is that you are considering for the membrane MR1, MR2, quite interesting compared to the traditional one. By the way, you have to consider that now that we have alternative system, all the traditional one are also, there is a lot of work to optimize it, to improve the performance also the traditional one. So you see here that already some traditional becoming much better, because there is a normal competition and people are trying to compete with the new one. But these membrane reactors are still better than also in this, the best available is also still on the lower value.
Isn't it better to have lower mass intensity?
Tell again?
So lower the mass intensity, the better. Isn't it?
Mass lower than mass intensity.
Well, so if mass intensity is lower, isn't it better?
No, if mass intensity is lower, it's worse compared to the membrane reactor in this case. For how is defined?
It's amount of mass per...
Mass of the specific product you are considering compared to the total that is entering. So that, in this case, what does it mean? That we are producing for the product that we are supplying to the reactors, the amount of ethylene we are producing is higher than the one that takes place in the membrane in traditional reactors. That's what we are telling.
So how I understood it is it means it takes 8.6 kilograms of reactant to produce 1 kilogram of ethylene.
Yeah, that is what, if you're looking to the definition we gave before. Yeah, mass intensity. What you have to consider that is the total mass that you are feeding to this system, and what we just extract of the product. So just that's the benefit. So we are producing more of this specific product we are considering compared to the total mass that is there. So it's less conversion basically. Okay. Okay, and you can define in different way this kind of situation in terms of the reaction yield, for example, and this the carbon efficiency. That means how much is really converted, and how much is becoming ethylene from the gas, and also in the carbon efficiency. You have this much more is produced compared to these other numbers. Basically, that is the point. And okay, so just to give remember that more and more you will see in the literature, hopefully, this kind of analysis. And when you read exergy, it's not a mistake of in typewriting. It's exergy. So you have to go back and learn what is exergy eventually, and you will learn that exergy is particularly interesting and necessary when you are analyzing integrated system, If you're analyzing a single unit, no, there is no big necessity to talk about exergy, about energy. But when you have a system in which you have one unit, in which the performance of the unit is related to what is happening upstream or downstream, and to the temperature of the system, of the other system upstream, or the other system downstream, so there is a big interrelation between different units, exergetic analysis are becoming very, very important. Because otherwise, if you normally analyze step by step, in terms of energy, you can make big mistakes, because you don't realize how much eventually of energy you are losing, or how big can be entropic losses related to the fact that you have difference in temperature between one step and the previous one, or one step and the next one. And that's what is changing the situation. And that's why you have to analyze, when you have a system, if you have to analyze, and today you always are looking to a system normally, the exergetic analysis is becoming more and more important. We have been discussing already that in terms of membrane reactors, the most utilized today on large scale, the most already successful, all the other ones I was discussing are interesting, a lot of reference, a lot of work in progress, but if you want to see in a petrochemical industry a big water gas shift or steam reforming, you have to go to the research corporate center eventually. You will find also big plant, but not the one already running in industrial level today, or just recently. I don't know if maybe today something new is happening, but that is the situation. Vice versa, if you are looking to membrane bioreactors, where the catalyst is a biocatalyst, so is a protein with catalytic activity, in this case is called enzyme. When you listen about enzyme, and we are working, in our nature there's a lot of enzyme working, these are biocatalysts. They are specific protein with specific properties able to operate as a catalyst better than the catalyst, the traditional one. They are very specific, they are very interesting, they are very fast sometimes, but they have a lot of problem. We mentioned already a little bit already, they have a problem in long lifetime. They lose very quickly their specific activity. They can be inhibited in their function by a lot of different chemicals. And they also have some relatively complicated mode of operation. They have a specific temperature at which they operate with high activity. They have a specific pH in which they operate. Most part of the enzyme that you will have to utilize, when you have an enzyme in your hands, you need also a buffer. Buffer is that you have to use this enzyme in a solution where the pH is very well controlled. You know what is a buffer? Buffer is a chemical solution able to avoid change of the pH for small addition of acid and bases. You define when you are in a chemical class. And always, an enzyme operation is combined with the presence of a specific buffer able to keep the environment at a specific pH, the one in which the activity is the highest one possible. So there's a lot of small problem not existing for the metals normally, or for the traditional catalysts. So we have to know about these things. But in the meantime, they are quite interesting because they are very specific in their activity. So they are not very general. They don't do you have enzyme able to break some compounds, some other protein. So you have a lot of protease, lipase, and urease, etc., that because they are able to operate on urea, they are able to operate on the lipase, on the lipids, etc. Very specific interaction with the reagents. Reagents, normally in this case, as I mentioned already yesterday, are called a substrate. And the property of this enzyme normally very, very high reaction rate, mild reaction conditions. They operate not high except a special enzyme. Today, some of you will study how to have enzyme that can operate high temperature. Some exist in nature, in the Vulcan region, that is these we call thermophilic bacteria, but not very expensive and not very easy to collect. They have very specific specificity in the reaction. They can be also stereospecific, they can address some conversion they can form level form or right form, for example, and they can also have a geometric specificity, stereo specificity, geometric specificity, very much more selective than the traditional catalyst we are looking together today. That's why there's a lot of interest to utilize this system in the industrial level, but for doing this, they have to be normally immobilized, because if you don't immobilize them, the lifetime normally is very low. All the enzymes working in our body, and we are full of enzymes, are normally already immobilized in some membranes, by the way, or they are compartmentalized. That means they are working in a very restrict environment where the level of freedom in the reorganization of the molecular structure is very limited. Because the catalytic activity, catalysis is a problem normally of interaction of your chemicals with some specific active sites. There are some parts of the molecules which are specifically ready to interact, to active, and for having a good reaction, two molecules have to approach each other, and when they approach, if you are able to give a specific orientation to your molecule arriving, you put the orientation in the right position, such a way that when they meet in the right way. And that will make easier that you are decreasing the activation energy. Otherwise, you have to rotate the molecules and trying to reach the right approach between two molecules. When you have to rotate, is energy consumption. The catalyst is decreasing the amount of energy necessary to have a positive approach between two different molecules through the active sites of each one of those. So that is what is happening with the enzyme. You can just realize one of the best way to to stabilize this enzyme is just making artificial membranes loaded with this biocatalyst. And so you have a per-selective membrane, and you can have a per-selective membrane in which some catalysts have been immobilized. And when the substrate is arriving, specific substrate will be converted, and it will have a specific interaction with the substrate of the reagents, and will be specifically converted. And that is quite interesting, and there is a lot of enzymes that have been realized in this way. Also here, as we discussed already before, you can have two kinds of the membrane reactors. You can have membrane reactors where you have inorganic membrane system, and they can operate high temperature, or that's the one that you can have biological membrane reactors in which normally we don't need the inorganic because these typical enzymes are coming from nature, and temperature is a mild temperature in our body. Only one working is roughly, if you don't have any disease, it's 37 degrees centigrade roughly. So that is a very low temperature. And that you can realize in two different ways. You can have an external membrane system in which here you have the reaction, and the reactant will go in this membrane system, which is separate from this reaction vessel, or you can have just the membrane itself, which is where you immobilize the catalyst. So that is just a system in which the mobilization of the enzyme is taking place in the membrane itself. There is no compartmentalization as in this case here. Reactor with membrane acts as a catalytic and separation units in one step. Reactor combined with membrane separation units. That's the one we are more interested and we are discussing about. If you are looking to this kind of system, you have to rearrange a little bit your knowledge in terms of the kinetic of the reaction that are taking place in kind of situation. Nothing different in reality from what we have been showing yesterday, looking to the different steps that you have to follow to describe what is happening in your system. Traditionally, however, the biologists have never been discussing too much with chemical engineers, and so there is two different, at the moment, two different way or equation or names to remember, because for the moment still these two words are separate. So when you're talking about enzyme, you're talking about Michaelis-Menten equation, you're talking about substrate instead of reagents, you're talking with using linear Bork equation, you will see. If you start from scratch, from the beginning, and you analyze the system, writing the different reactant, how they are converted, and what is the product, and you write the equation, the kinetic of single step, at the end is exactly the same story. But if you go through the literature, you will find different name, different tradition, so you have to learn and to understand what we are talking about. For example, the traditional reaction that you have in a bioreaction, you can have your substrate that is becoming products. And in this case, the reaction rate, the definition in this case is all the same. There's nothing different. The reaction rate is nothing more than the change, the derivative of the concentration of your substrate in a function of time or of the product. So this one is disappearing, so there will be a minus in front. This one is appearing, there is a positive in front. So that's the definition that you are giving also for any kind of chemical reaction. But the next step is which kind of mechanism you are considering. There is one kind of mechanism, kinetic mechanism, that is called the mechanism of the activated complex. There are different theoretical modeling of how the chemical reaction takes place. That is one typical example where you have your substrate and the presence of your enzyme, and you have a kinetic transformation in the final product. And the enzyme, as you know, is a chemical compound which is changing the kinetic of the system, but does not take part of the stoichiometry of the reaction. So the enzyme is not disappearing. The same enzyme you have here, the gram of protein you have been added has to be down here, otherwise not an enzyme. The enzymes are just not taking part to the reaction, are just decreasing activation barriers in the reaction, but in some cases you don't write here, they just put the enzyme on this line, showing that they are not part of the stoichiometry of the system. In this case, they don't, in biology, they put the enzyme here plus substrate. There is a direct conversion to this one through this ES. This ES is this activated complex. It's a combination that you cannot see in real life. You don't have be able to detect any concentration of this substrate enzyme complex. That is hypothetically, in the modeling is assuming that you before becoming a product, you have a formation of this ES and decomposition of ES through the kinetic constant K2 in, again, the enzyme that at the end has to be present in the same concentration, and S now is becoming a P. But we are assuming this ES as an intermediate activated complex, exactly as in traditional modeling of other chemical reaction, also when no enzyme is present. Okay? And that is the situation. This equation assuming that you are in a situation in which the product is much less than substrate, that means just in a starting of your reaction, so there is no back diffusion. Now this is an equilibrium, as you see here, which means that in the time that your substrate is becoming product, the product is going back through K minus 2 and K minus 1 and reforming S. So there is a dynamical chemical equilibrium. All the chemical systems are in a dynamic equilibrium. Apparently nothing is moving from a macroscopic system, but if you are looking at molecular level, there is a lot of things happening. That means continuously this S is transforming in P and P is retransforming in S. At one point when the two velocity of formation and disappearing are equal, you are in equilibrium, in state of equilibrium, and that we call dynamic equilibrium. Dynamic because everything is moving. When you are starting this operation, that means when P is very, very low concentration, this velocity back is still very low because the velocity is directly related to the concentration of P. So in this situation, this is the expression you can write. In principle, the velocity is proportional just to the concentration of this transient compound that you cannot see, but that is roughly the situation. On the basis of this, you can just make some approximation, and you can try to have an expression for this ES that cannot be measured. Maybe does not exist because we don't know. Nobody has been today. By the way, in some case you can also see something. Today there is what is called a phantom chemistry. I don't know if you are familiar with the fact that recently some people have received Nobel Prize because we have a new system, a new device that are able to identify transformation in a period of time which are phantom chemistry. That means seconds minus 15, minus 12, etc. So incredible fast. So in phantom chemistry, in some time we can see also the formation of these intermediate compounds. But normally this is not easy case. So you assume that, as written here, we cannot measure, basically. We cannot see in reality. We have to make an hypothesis, assuming the formation of ES, and on the basis of this hypothesis, we see which constant ways we will have, which is final product, and if there is a good agreement with the results and the modeling, we like the hypothesis that ES is being formed. Otherwise, we have to change the system and find some other modeling. Anyway, so we can assume a steady-state kinetic condition, which means that S and P are changing, but ES does not change. And that can give you this kind of mathematical expression. And we have that this E total is equal E free plus the one that is bounded in this transient system. And now you can make, and we don't make, a lot, you will find in your notes, a lot of this transformation divided by, and ds in the t is equal 0, etc., 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 etc. You can have the V formation, the V breakdown, and you have the equality, because formation disappear in steady state that must be equal, and so you can have this kind of relationship, and you can rearrange and solve for ES, and that would be expression of this concentration of the hypothetical concentration of the transient complex. And now you can introduce some definition, and that's an important one, because when you are doing this work, you always will learn, you will characterize the behavior of your enzyme through this Michaelis-Menten constant. And the Michaelis-Menten constant here is just the ratio between the K2 plus K minus 1 on K1. And K, remember, the kinetic constant of different hypothetic reactions that are taking place. And now if you substitute this Michaelis-Menten constant in this equation here, you will have this kind of, and you remember this equation that we wrote before, you will have this kind of expression, and another expression will be here, and will be at the end you will have this kind of relationship. In this kind of relationship, basically, where you have been solving for ES, and you have an expression for the reaction rate in terms of all known quantity, because this is the concentration of your substrate, and you know it, you just made by yourself. This is concentration of the substrate. This is Km, and Km, the Michaelis constant, we saw how it is, and that is a term that we will see can be easily measured. And this is the concentration, the E, and we know that is kinetic constant. All these terms are known, so you can just analyze this system. And there are situations in which, as we discussed in terms of traditional kinetics, you can have kinetic control or diffusion control system, depending between the value of the concentration of the substrate compared to the Michaelis-Menten constant. And the enzyme can be saturated with substrate in some situation, and basically Km is equal to S, to the concentration of the substrate, and so the equation becomes just V0 K2 per E total, and the easier way. Basically, at the end, that is the equation that you have to remember. Typical vision is this V0 is a Vmax for the concentration of the substrate, concentration divided substrate concentration, and Michaelis-Menten constant. Now the point is how to measure Michaelis-Menten constant and the Vmax. And this is basically one thing that is traditional for the biologists. That is, you can see here that the relationship that we wrote here means that at low value of the substrate, V0 is linearly proportional to S. And that means the S is equal to Km. And which means that at the end, in assuming these different hypotheses, you have to follow. By the way, here there is a protocol just to learn how to do it, because there's everybody working with this kind of membrane has to learn and follow this one. Normally you run a series of reactions with constant V0 T, and you only measure, you change the concentration of the substrate, and you measure the velocity of your reaction. After you make a plot, where you plot this V0 that you have been measuring as a function of the substrate concentration, and now you'll see if you make this, there is a nice plot from which you can estimate this Vmax that is present in our equation, and you can calculate Vmax divided by 2, which is related at the end of the Michaelis-Menten constant. This is the kind of plot that you have. You plot here the product concentration that you can measure continuously during your reaction at different value of the concentration, and here is reaction time. And you have this kind of numbers that you will measure at this one. This is the velocity at the starting point when there is no back diffusion. And that is the V0 that you want to obtain. Now from this picture, you can define this asymptotic value here, that is Vmax. Max transfer velocity you can obtain in your system. And at 50%, this V0 is Vmax divided 2, and that basically is what we call Michaelis-Menten constant. That's why I said that all these things are nothing, there's nothing different, and you will obtain exactly the same results if you have the same approximation, and you do the kind of exercise we described yesterday, that you write your concentration of species I, species B, you assume there is a conversion, you make the maps balance, everything is the same. In biology, they learn doing these millions of experiments that generally if the system can be described from the equation 1 that we wrote down, assuming the formation of this activated complex, etc., at the end of the story, you will have this kind of graph. In this kind of graph, if you can detect what is the maximum velocity, you take the alpha of the maximum velocity, and that is this V0, and you just, when you have a V0 here, you go down here, and that is Km, the Michaelis-Menten constant, okay? So relatively easy if you know all these things. And that is one way of doing. There's another way of doing the same data. You can replot the same data in a different form. Instead of putting the conversion as function, you plot 1 on V0, so the reverse of the velocity that you measure, as function of 1 over S. And you obtain what is called linear Haber-Bark plot. Linear Haber-Bark plot, in which you can see here again the intercept here on the ordinate is the Vmax, 1 over Vmax, and this intercept here is 1 over Km. And that is coming from this analysis. And that is another way where everything is the same, it's just replotting, and it's much easier sometimes to extrapolate in this case than in the previous one. And that is the way to obtain this Michaelis-Menten constant and the max velocity of the system. If you have to do something in the lab on enzyme, you have to learn quickly, because all this kind of way of doing is the one that all our students, they go through, and they have a protocol in which they learn step 1, step 2, step 3, because that is very well accepted. Eventually, there is still another manipulation of the Michaelis-Menten equation, as done by this guy Hedy and Ofsti. Nothing new, except in a different, better visualization of the data, and you minimize the error just using this kind of plotting, which what you plot here is the V0 on the abscissa, and here is this V0 divided by S, which is a different way of writing the same equation. That is a useful, in some case, this idea often, because it's much easier, you don't make too much mistakes when you extrapolate in this way. It's a linear extrapolation, there is no hyperbolic curve, etc. You know, in this previous, you have this behavior here. And normally to tell where exactly Vmax, the probability, if you want to be very accurate, is not difficult to make mistakes, because you have to extrapolate this, etc. And if you are a very good experimentalist, it's okay. If you are not a very good experimentalist, you can make some mistakes. But that's why you can have this other form, this Hedy-Ofsti, and that is a better way of doing, because you easily extrapolate on here, Vmax over Km, and that is just Vmax here. Okay? And if you know the Vmax here, obviously you know also Km. Or the slope, the slope is 1 over Km. So you can extrapolate Km easily when you just plot in this way. Okay? So that is benefits. A linear bar plot, clear separate dependent and independent variables, and that is one of the motivations for doing this. Okay, this is just again the protocol that you can have to follow, just to tell that this is a standard way of doing. Remember that in the membrane reactor where we have a catalytic membrane system, you will have exactly the same kind of phenomena that we have been describing in normal reactors, including this concentration polarization. That means a change of the concentration of substrate and products at a certain distance from the membranes and from the support. So nothing is changing, so you have just to consider this, and you can have a different kind of presentation. That is the typical, again, the equation we have been assuming at the beginning, and we assume that there's a story. That is the kind of behavior that you can obtain, and that the system at the end can be just reanalyzed exactly as a normal catalyst. So I skip this part because we're just repeating things that nothing different from what you learned already. That is a typical profile, theoretical, that you can have no change in concentration approaching the membranes, but in real life you can have this different situation. That means the concentration here is very different from here. So you have a change in driving force and change of the concentration. That's typical concentration polarization kind of phenomena. And you can reanalyze the same story with the different number that we have been able to introduce. And basically also here we need to find criteria of efficiency, because the enzyme can be immobilized in the internal surface of the porous supports. And so we have to know if this can be inducing some lack of efficiency. We can change the permeability of the system, and we can have in induce situation in which we can have kinetic control or just diffusion control. That means the system is slowing down the velocity in which the substrate is arriving on the catalyst, because there is a mechanical restriction to the system. And that's something that we can define again in terms of effective diffusivity, exactly as we defined yesterday, compared to the apparent diffusivity. Are two different terms. And also here you can have Thiel modules, in which Thiel module is nothing more than the ratio between the reaction rate and diffusion rate. And so from the Thiel module, you can identify if the system is controlled by the reaction rate, by the velocity of transformation of your substrate, or by the velocity that characterizing the arrival of the substrate to the active sites. So if the system is not very efficient, you can slow down the velocity of the transfer of the reactant to the diffusion to the active site, and you block the reaction for this. This becomes the controlling step. You can have two extreme cases, diffusion rate or reaction rate, exactly as we saw a little bit yesterday. Okay, and okay. All these membrane reactors are the same characteristic of the traditional membrane reactors. I was mentioning already that these are interesting. Most part of the fermentation process, which is part of the story here, are normally batch system. Just batch system, so this continuous process. When you are working with membranes, everything becoming continuous. That's advantage number one of all the membrane reactors are continuous system, no batch anymore. And that's important, both in this continuous tubular reactor in the bio, exactly as you can have in the other system, or in a continuous tank reactor, something entering and going out. And there is a lot of possible application that you can be already listed here, much more, and all these are industrial. All this one already been improve juice yield and better color extraction in the fruit juice industry, or lactase. I was mentioning this low lactose milk ice cream, a better product for special dietary food where you want to avoid lactose because people we don't digest, etc., etc. All these are just system. Basically, these advantages are the possibility to have a much easier method of purification and to decrease the cost, just because the biocatalysts are expensive, and the separation from other reagents when we have this system immobilized. All these problems are just solved by this immobilization. Also, the immobilization can be an area of research. Here you see some way, this is the external system, there is no big trouble, but here you can entrap your catalyst. That is a typical example of mixed matrix and membranes. You can entrap your catalyst during the membrane formation, or just by jellification on the surface, or just by chemical bonding, where you must be careful because chemical bonding by cross-linking normally is also changing the specific activity. So if you want to have the cross-linking by chemical bonding, which is interesting because it's very stable, but you must be sure that it really does not change too much the specificity of your protein. And that's also the other way, this bounding through physical absorption, ionic binding, or chemical or covalent binding. These are less dangerous in changing the properties. This is the more dangerous one. But anyway, people are studying and realizing different way of doing and trying to improve the performance. Again, example of a lot of this system. I was just to arrive to the most interesting one. And first of all, remember that you can use flat sheet membranes, and initially all the membranes were flat sheet, but in this case, but today, more and more, this is a membrane reactors. This is a system in which we have been immobilizing, in this case, the dense skin of this asymmetric membrane is inside. So what you do is just to ultrafilter a protein solution from outside to inside, so the protein cannot penetrate across the dense skin. The water, the solvent is going through. So what is happening at the end of the ultrafiltration of this nice hollow fiber module, that you will have all the spongy part of your membranes filled with the protein. And these membranes, these protein, once they are here, they don't move. If the back diffusion is very, very slow, it will take months or years before one of these things will go out again. And so that is kind of immobilization. Now, if you are able to well optimize the percent of a protein that you distribute in the spongy part, such a way that there is no big flux decay, you can later on, instead, you can put your substrate from here, and the substrate will meet the enzyme, reaction will take place, and the product will go across. Or you can also try to have from the other side. In the other side, there is the risk that you can remove much faster eventually the enzyme from here if you have pressure drops in this direction, but normally you can be able to control. What you have to be careful that this amount here is not infinite. Normally that can be on the order of 20%, 30%, 40%, more than 40 you can start to have some leakage. And that is not what you're looking for. But there are different ways of doing and to control this kind of situation. That is the one thing I was mentioning already that has been studied. You can also try to take in profit of the concentration polarization I was mentioning before. You can gellify, so you can arrive at a certain level of concentration of your protein, and you just go from a solution to a gel. And the gel can be just an additional layer on the membranes, but gel are relatively permeable, and so you can have a gelled, immobilized enzyme reactor, dynamically formed eventually. So there are different this kind of formulation that you can study, and there is a lot of this kind of operation that can be utilized. Sorry, this is application in all these different fields. And that's the most interesting. You can have I've mentioned already that the enantiomeric production is becoming today a very important area of research, and you can be very careful. By law is controlled very much in the pharmaceutical area, but the same problem exists also in food. In food at the moment people are less aware, and there's less problem for different reasons, because the food we are using is very well known for a long time, so we know how to handle. When you produce a new drug, sometimes it's new synthesis, and we don't know too much, and so there's a problem. But that's this possibility to have an enantiomeric production. That means to produce only one form of the different, from the different racemic is very, very important. In a country as India and Pakistan, etc., this story has been at the origin of the thalidomide problem, etc., huge trouble for the, and that was just at that time there was no way to have an enantiomeric production. You were producing both forms. Enantiomeric means, for example, this is the case of naproxen that most of you are using. I don't know if you are familiar with. And the naproxen basically is the S-naproxen is 28 times more active than the R-naproxen, the level form compared to the right form. This is talking about only activity. In some case, you can have that the S form is giving positive effect, and the R form is killing yourself. Typical example can be limonene. You can have, depending from if you have level or right, one is sweet, the other one is sour. You can have very big difference. The same chemical, when you write the formula, nothing change. It's only that you have a steric difference. Now this is the problem of my hands. Now we have some specific enzyme, lipase, from Candida rugosa that, that preferentially hydrolyze the S-naproxen ester. Now if you know this and you learn about, you can just have the production only, basically only, of this one of the two. Because you can have a membrane reactors in which you immobilize your lipase in the membrane system, and if you go in literature, you will find a lot of paper by Dr. Giorno, myself, etc. in this area, in which you just have what you have as substrate is the levo and the right form. But if you put in your membranes the appropriate catalyst, the specific kind of lipase, the only conversion in the acid is on the levo form. And so on the other side, there is no, this naproxen methyl ester R is basically not converted, only this form is coming across. So what you have across your membranes is only this form here, and this form here basically is zero, because the catalyst that you immobilize in this membrane is able to operate only on this R form of this ester. And so you can convert one compound only and separate continuously. If you use a normal system, impossible, you convert, but they are mixed and they are also the other present. And if you have the final result here, that is the situation. You see here, nothing happened with this form. The R is zero conversion, and you just produce the S, if you're doing right. And that's what we call, you can replot the production, the enantiomeric excess, basically. That is, that is the point. That enantiomeric excess is approaching 100%, it's 99.5, 99.7, okay? So this kind of concept can be very well extended to a lot of other kind of situation, and this system works very nicely. And I told you, people don't know, because on this kind of things there are no big advertisement or marketing, but when you buy a drug, for example, ibuprofen, which is very, very popular. Ibuprofen is an anti-inflammatory agent present in most parts of the pills that instead of aspirin today, you take very often ibuprofen. Ibuprofen is produced 100% with this kind of reactors, because one of the precursors of the ibuprofen, which is very unstable and is has a problem of an enantiomeric excess, and diltiazem is the name, is produced through membrane bioreactors, immobilizing one form of lipase, etc., and this is on the market. Nobody's telling you because the people don't understand, they can be afraid, but that is the way in which you are doing for preparing this kind of system. And on this one, there is a lot of interesting other opportunity, for example, to increase the efficiency of this penetration of the substrate in the enzymatic membranes. We are also, you can operate making microemulsion. You produce some emulsion based also on membrane system, by the way, mono-disperse nano-emulsion in which you can mobilize your substrate that is penetrating across your membrane for giving at the end very high. You can just control interfacial problem and then you can minimize the loss of this substrate in the system, etc., etc. Okay? And there are a lot of these motivation or change in this kind of system. Remember that, as you see, I wrote 3 times the same equation. Every time you are discussing these things, you start from Michaelis-Menten equation. That is the hypothesis of the back. I'm showing this because we don't know if all this is correct, because this is an area where a lot of work has to be done. And today, chemical engineers normally are, as I mentioned to you, they work on this combustion problem, and they learn that for transforming C plus oxygen in CO2, there are 4,000, 5,000 different steps. For this kind of reaction, we are always writing the same equation. Nobody knows how many steps we have in transforming the substrate in the product. But we know this problem is much more interesting and to understand than the CO2, because this is for our life. And we can have the problem of drugs and food that are going in our body, and they have a lot of interaction, and they go through before forming this. But we always write the same equation because this is much more complicated to understand, and everybody for the moment is working here. Not really true. A lot of research is in progress, but the standard equation is the Michaelis constant equation. This is the kind of assumption we are doing. We are forming this activated complex that we assume it exists, but we don't really know, etc., etc. So I mean that there is a lot of work to be done, and for understanding the real velocity that characterizes the transformation of our interest, assuming that there is or not there is some competitive reaction. We wrote one reaction. We don't know the competitive one. We can have some other reaction taking place. That should be interesting to learn. That is one of the basic assumptions for modeling the system that you can start to do it, because now when you go in detail, introducing the membranes that at the time of Michaelis-Menten were not existing. So we know that our membranes are all asymmetric. So we have a dense skin and you have a spongy layer. As you remember, I showed you before in the slides, in the spongy layer we mobilize our catalyst, our enzyme. So that is the real system we have to analyze. And now you can start to work in this system and writing this Michaelis-Menten equation in the skin layer, the Michaelis-Menten equation in the spongy layer, and trying to do a little bit more than what exists in the traditional books of biology, and trying to understand this is the term, because nothing happened in the skin layer, we only have the diffusion, and here in the spongy layer we have the conversion, because there is a catalyst, and you are assuming all the catalyst in the spongy part, and if you do this, now you can just develop the equation and try to calculate the mass transfer across, and that is the diffusivity, etc., and you will arrive to some J over in a function of the Thiel module also here, and you have this kind of behavior, etc. So this is another area in which membrane engineers are starting to try to make some progress compared to what exists in the traditional literature, and a lot of work has to be done, by the way, and this is a typical example, but this is just something that a researcher are doing today. The most interesting, we are using the last 5 minutes, eventually we will talk again on Friday, application, however, all this interesting thing is this one. This one is no more an interesting way of doing, But this is what we call in Europe best available technology, which is nothing more than applying part of the understanding and knowledge of these bioreactors to the treatment of the municipal wastewater. And that's just an integration, exactly the same kind of system that we have been looking at. But that is the activated sludge. That means the typical biological system that people are using today and we're using until yesterday everywhere, where you have some microorganisms, but they are supposed to transform all this dirty stuff that is present in the municipal wastewater through decomposition in ammonia, in nitrogen, etc., etc. And you can improve significantly the efficiency of this system here just by combining this system with traditional membrane system. The role of this membrane system here is continuously, as we saw in the hydrogen case, nothing new, so there is exactly what you learn very nicely already, that you can just continuously remove some of the product of the reaction. You have here degradation, you send on the ultrafiltration units. Most part of the heavy stuff does not permeate your membrane. Some of the components, solvent, and some of the product obtained by decomposition, again ammonia or some other compounds, will go through. So you continuously increase the efficiency of the operation of the microorganism or enzyme present here. More than this, you eventually, also in this kind of configuration, you can recirculate also part of the concentrate, and so you just keep the eventually higher concentration of the catalyst, of the microorganism. That also is increasing the performance. But that was the traditional way of doing initially. Already we were doing this in the 70s, 75, etc., working in some situation in the later, in Spain, people were working this in the leather industry, for example, or in the pig factory, where you have thousands and thousands of porks, and that was the way of doing to minimize and to increase the efficiency. Today, that's much more sophisticated, because what is happening, there are a lot of problems here in fouling, in heavy stuff, and cleaning the membranes is a big problem. No one wants to. Smelling here is incredible bad if you're just working in this area, etc. Today, Japanese, they invented a very simple, intelligent way of doing, because what they are doing, this part of the story, instead of being external, they took this one and they immerse in here. So exactly the same kind of operation, but this is immersed. With one change, if you immerse here, what you are doing, instead of pressurizing, as we are doing here on the membrane surface, you make vacuum inside. So what is happening, that making vacuum inside, you can extract the product inside the membranes, and that is the clean part. You clean already most part of the product, and that is what is called submerged membrane bioreactor. And the fact that this is immersed here is a way to minimize easily fouling problem. This aeration here means that here there is a double phase. You have also one of the way to control, we mentioned studying the fouling problem, is to inject micro bubbles of air on the membrane surface, so it's a mechanical way to remove any deposit that you form on your membranes continuously. So depending from the velocity, from the size of the bubbles, etc., you can have a very good control of fouling. So that is a quite interesting concept that when it was introduced in the 90s, today is the best available technology for this kind of specific application. In prospective was Mr. Yamamoto, that is just the one that was here no, he was in Japan really. But anyway, it's still very active at Tokyo University. And what is interesting, this concept today is not only for municipal wastewater treatment. You can now introduce in any industrial process, you can have the same concept upstream, not just at the end of the story. And that's becoming quite attractive, because you can have a lot of situations. Well, that is a traditional way of doing the classic sewage treatment process that people were using one time, and that now has been combined. Here is written micro ultrafiltration operation combined with biomass treatment. It's not so anymore. This can be membrane distillation. That can be nanofiltration. depending which kind of separation you want to obtain, and if you want to be more sophisticated than what here, you can just change here, and you can introduce any kind of membrane operation. And particularly if you go in little on the web, you will find already MD or nanofiltration, that much more severe separation and control of the quality of the permeate that you must have. And what is more interesting, that instead of having this one as for controlling sewage treatment, you can have in a big chemical process, very upstream, in which you can start to optimize some process. In biomass, typical example is biomass production, where there is a lot of biofuel, things, in which this kind of reactors can do the job. And anyway, that is some of the benefits that you have. That's one of the concepts that can be done with flat sheet, hollow fibers. In some case, that's quality of the water. This, effluent quality is quite interesting, very possible to have direct reuse. Very small footprint. These are not people expert in process intensification, but if you read what they are suggesting, small footprint, this is 950%. You can make half the size of the normal plant. Easy to control, can be just a remote control, less large production, 40% less. So you remember this is all consistent with the process intensification logic, and that's the reason. Immerse module of external module, they're both configuration, and some of the data you can see here. By the rules, what you have to respect was, I don't know, COD. Well, COD here is roughly the same, but TS 35 you can have a 5. TN basically that is no, there is no regulation, but that is very low 1, and that is one plant. We have a full city in Italy. That's Brescia. Brescia is a city of about 120,000 people. All the final effluents are just going through one of these plants. They're just submerged membrane bioreactors, and that is becoming more and more. The cost here, as you can see here, that's a 70% as still energy, so you have to find to save more energy, and the rest, the membrane cost is relatively small, 8% of the total, so it's not real. That is again, that's in Venice. In Venice, still you can have some industrial units running just because that is the largest in Porto Marghera, just on the back of Venice, the industrial part of Venice, but still you can have some industry because this thing is working. And the quality is so good that basically you can still keep the industrial activities in Venice, but only using a very well-designed and large-scale MBR system, and etc. Okay, we stop here, and we will meet on Friday morning. Any question, any problem? All okay? Good. We meet on Friday. Thank you for the tea.